Some theories of parallel universes suggest that we can detect these universes through gravity leaks from one universe to an adjacent universe. For example, the gravity of invisible objects residing in parallel universes only millimeters away may distort light from distant stars. The entire idea of multiple universes is more plausible than it may sound. The American researcher David Raub polled 72 leading physicists in 1998 and found that 58% of them, including Stephen Hawking, believed in some form of multiple universes theory. Many flavors of parallel universe theory exist. For example, Hugh Everett III's 1956 doctoral thesis, The Theory of the Universal Wave Function, outlines a theory in which the universe continually branches into countless parallel worlds. We refer to this theory as the many worlds interpretation of quantum mechanics, which asserts that when the universe, world, faces a choice of paths at the quantum level, it adopts various possibilities. If the theory is true, then all kinds of strange worlds may exist in some sense. In several worlds, Hitler won World War II. Sometimes the term multiverse suggests that the universe we can readily observe is only part of the reality that comprises the multiverse, the set of possible universes. If our universe is infinite, then identical copies of our visible universe may exist, with an exact copy of our Earth and you. According to physicist Max Tegmark, on average, the nearest of these identical copies of our visible universe is about 10 to 10^100 meters away. There are an infinite number of copies of you and your variants. The chaotic cosmic inflation theory also suggests the creation of different universes. Perhaps countless copies of you existing, but altered in fantastically beautiful and ugly ways. In 1952, researchers discovered that iproniazide, a drug under development for tuberculosis patients, was effective in treating depression. 3 years after its approval for use in 1958, serious liver damage led to its withdrawal. In 1955, imipramine was being considered as a treatment for people who have schizophrenia at a mental hospital in Switzerland, but the results were not positive. Psychiatrist Roland Kuhn decided to try the drug on 40 depressed patients, and the results were all positive. Patients became livelier, their voices were stronger, they were able to effectively communicate, and hypochondriacal complaints all but disappeared. He published his results in 1957. Imipramine moved to the market under the brand name Tofranil. It was the first of what soon became a family of drugs labeled tricyclics, so named because of their 3-ring chemical structure. Tricyclics work by inhibiting the reuptake of the neurotransmitters norepinephrine and, to a lesser degree, serotonin, thus initially making more of them available for use in the brain. There can be unpleasant side effects, however, such as dry mouth, constipation, weight gain, and sexual dysfunction. Soon after, researchers discovered imipramine, another antidepressant that also functions by inhibition. The class of drugs known as monoamine oxidase inhibitors, MAOI, prevents the action of an enzyme, monoamine oxidase, which breaks down neurotransmitters such as serotonin and norepinephrine. Today, doctors rarely prescribe MAOIs due to their even more dangerous side effects compared to tricyclics. The US Food and Drug Administration approved Prozac, a second-generation antidepressant, for use in 1987. Prozac and other drugs like it are selective serotonin reuptake inhibitors, SSRIs. Just as their name implies, they inhibit serotonin reuptake in the synapse. Prozac's response has been phenomenal. Within 3 years of its release, psychiatrists prescribed it as the #1 drug, and by 1994, it ranked as the second best-selling drug globally. It does not have many of the side effects of other antidepressants. Indeed, millions of people who have no mental disorder at all use it to enhance their personality, lose weight, or increase their attention spans. Think about your typical satellite, such as a photographic satellite that takes pictures of the Earth. On the one hand, it is simple. It has a high-resolution digital camera attached to a telescope that acts as a lens. It has solar panels and batteries to provide electricity. It has an antenna and a radio to communicate with Earth. There's nothing really surprising. You would expect to find these parts on any remote camera system. The camera itself, a power source, and a radio link. So why does a satellite like this cost millions of dollars? This is largely due to the special considerations of flying in space. Engineers have to keep the satellite functioning in an inaccessible, harsh environment. Russian scientists faced these challenges when they launched the first space satellite, Sputnik 1, in 1957. Since then, satellites have gotten far more sophisticated. Take, for example, the computer in a modern satellite. Engineers cannot use a normal computer in space. Everything must be radiation hardened at the time of manufacture to prevent cosmic rays, solar particles, and other forms of radiation from disrupting the circuits. The computer will then be triple redundant, with a voting system to detect if one of the three fails. The satellite has to stay properly oriented at all times. It usually does this with a combination of sun trackers, star trackers, and reaction wheels. The reaction wheels can speed up or slow down to change the satellite's orientation. There will also be thrusters and plenty of fuel, e.g. 300 pounds or 150 kilo, to last a decade or more. The solar cells are not typical. They are radiation-hardened, high-efficiency cells. Also, the batteries are different. Engineers have created special nickel-hydrogen batteries that handle tens of thousands of charge or discharge cycles and can last more than a decade. Finally, there is a significant amount of reliability testing, certification, and redundancy, which includes assembly in a cleanroom environment, testing in a powerful vacuum, and vibration tests, among other procedures. The satellite must function in space for many years without repairs if something goes wrong. This work and these special components make any satellite an expensive proposition. In 1958, 5 years after Watson and Crick discovered the molecular structure of deoxyribonucleic acid, DNA, the double helix, Crick proposed the central dogma of molecular biology, which he popularized in a paper in Nature in 1970. In its basic terms, the central dogma states that genetic information flows in only one direction, from DNA, transcription, to RNA, translation, and proteins. A section of DNA transcribes information to a newly assembled piece of messenger RNA, mRNA, which copies one of the two strands of DNA and uses it as a template. The mRNA then travels from the nucleus to the cytoplasm, binding to a ribosome. The ribosome processes the instructions into a codon, a 3-nucleotide sequence that specifies the sequence of amino acid additions to the expanding peptide chain. The final step involves the faithful replication of DNA to a daughter cell, carried out by mitosis. The sequence's original formulation never translated backward from DNA to RNA. Howard Tiemann at the University of Wisconsin-Madison and David Baltimore at MIT independently discovered the enzyme reverse transcriptase in 1970, upending the central dogma. For this work, Tiemann and Baltimore were co-recipients of the 1975 Nobel Prize. Subsequent research revealed the presence of reverse transcriptase in retroviruses like the human immunodeficiency virus, HIV, which facilitates the conversion of DNA from RNA. Furthermore, apart from the central dogma, not all DNA is involved in programming protein synthesis. We have not yet determined the biological function of the non-coding junk DNA that makes up about 98% of human DNA. Semantic issues were also raised. In his 1988 autobiography, What Mad Pursuit? A Personal View of Scientific Discovery, Crick commented that dogma was ill-advised. He chose not to use the word hypothesis, which, in retrospect, would have been far more appropriate. In this context, dogma refers to an unquestionable belief. Mary Bellis, a technology historian, asserts that the development of the integrated circuit appeared predestined. Two separate inventors, unaware of each other's activities, invented almost identical integrated circuits, or ICs, at nearly the same time. Today, countless examples of electronic equipment, from coffee makers to fighter jets, use an IC or microchip, a miniaturized electronic circuit that relies on semiconductors. An electric field can control the conductivity of a semiconductor material. With the invention of the monolithic IC, formed from a single crystal, the traditionally separate transistors, resistors, capacitors, and all wires could now be placed on a single crystal, or chip, made of semiconductor material. Photolithography, a method that selectively transfers geometric shapes on a mask to the surface of a material like a silicon wafer, is a faster way to make an IC than putting together separate circuits of resistors, transistors, and other parts by hand. The speed of operations is also higher in ICs because the components are small and tightly packed. Physicist Jack Kilby invented the IC in 1958. Working independently, physicist Robert Noyce invented the IC 6 months later. Noyce used silicon for the semiconductor material, and Kilby used germanium. Today, a postage stamp-sized chip can contain over 1 billion transistors. The advances in capability and density, and decrease in price, led technologist Gordon Moore to say, "If the auto industry advanced as rapidly as the semiconductor industry, a Rolls-Royce would get 500,000 miles per gallon, and it would be cheaper to throw it away than to park it." As a new employee at Texas Instruments, Kilby invented the IC during a late July vacation period when his employer's halls were empty. By September, Kilby had built a working model, and on February 6th, Texas Instruments filed a patent. The germ theory of disease, proposed in the mid-1800s, suggested that microorganisms cause many diseases, and people wondered how the body attempted to defend itself against such foreign invaders. Today, antibodies, also called immunoglobulins, are the protective proteins that circulate in our bodies and identify and neutralize foreign substances, called antigens, which include bacteria, viruses, parasites, transplanted foreign tissues, and venoms. Plasma B cells, a type of white blood cell, produce antibodies. Each antibody consists of 2 heavy chains and 2 light chains made of amino acids. These 4 chains bind to form a molecule resembling the letter Y. Variable regions at the 2 upper tips of the Y bind to antigens, thereby marking them for other parts of the immune system to destroy. Many millions of different antibodies can exist with slightly different tip structures. Antibodies can also neutralize antigens directly by binding to them and, for example, preventing the pathogens from entering or damaging cells. Antibodies circulating in the blood play a role in the humoral immune system. Additional immune players, phagocytes, function like single-celled creatures that engulf and destroy smaller particles. The binding of antibodies to an invader can mark the invader for ingestion by phagocytes. Tests to detect particular antibodies may lead a physician to suspect or rule out certain diseases, such as Lyme disease. Antibodies binding to the body's healthy cells can trigger autoimmune disorders. Sometimes scientists can make antiserums by injecting animals with an antigen and then isolating the antibodies in the serum for human use. Paul Ehrlich coined the word antibody, Antikörper in German, around 1891. He proposed a mechanism in which the receptors on cells attach to toxins in a tight lock-and-key fit to trigger antibody production. English biochemist Rodney Porter and American biologist Gerald Edelman won the 1972 Nobel Prize for their independent research, which started around 1959. They elucidated the antibody's Y-like structure and identified heavy and light chains. Laser technology has become important in a wide range of practical applications, writes laser expert Jeff Hecht, ranging from medicine and consumer electronics to telecommunications and military technology. Nobel Prize recipients received the award for laser-related research. Laser is an acronym for light amplification by stimulated emission of radiation, and lasers use a subatomic process known as stimulated emission. first considered by Albert Einstein in 1917. In stimulated emission, a photon, a particle of light, with the right energy, causes an electron to drop to a lower energy level, creating another photon. This second photon's phase, frequency, polarization and direction match the first. Reflecting the photons repeatedly through the same atoms can lead to amplification and the emission of an intense radiation beam. We can create lasers that emit electromagnetic radiation of various frequencies. In 1953, physicist Charles Townes and students produced the first microwave laser, MARSA, but it was incapable of continuous radiation emission. Theodore Maiman created the first practical working laser in 1960 using pulsed operation. Dermatologist Leon Goldman first used a laser in 1961 to treat melanoma, a skin cancer, and later he used related methods to remove birthmarks and tattoos with minimal scarring. Laser surgery's speed and precision have led to its widespread use in ophthalmology, dentistry, and other fields. A laser beam alters the cornea's shape in LASIK eye surgery to correct for nearsightedness and farsightedness. During prostate surgery, doctors may use a laser to evaporate tumors. Hemoglobin absorbs the green laser light, causing coagulation and stopping a bleeding blood vessel. A surgical laser's hot beam can cauterize or seal off open blood vessels as it moves along the tissue. Watson, Crick, and Franklin figured out the structure of DNA in 1953. DNA has 2 strands, each with 4 nucleotides: adenine, A, thymine, T, cytosine, C, and guanine, G. In RNA, uracil, U, replaces thymine. But how did the DNA molecule's genetic information translate into the biosynthesis of a protein? The Russian physicist George Gamow postulated that a 3-letter nucleotide, codon, could define up to 64 amino acids, more than sufficient to code for all 20 amino acids used to build proteins. In 1961, Marshall Nirenberg and J. Heinrich Mattei at the National Institutes of Health tried identifying the amino acid that would emerge from adding a single nucleotide to a reaction mixture. We produced the amino acid phenylalanine, cracking the first letter in the genetic code. Soon after, we discovered that adding CCC yielded proline. At the University of Wisconsin-Madison, Hargobind Khorana developed more complex sequences of repeated 2-nucleotide sequences. In 1964, Robert Holley at Cornell University discovered and established the chemical structure of transfer RNA, tRNA, thus providing the link between the role of messenger RNA, mRNA, and ribosomes. A ribosome first attaches the necessary information to tRNA, translating it into messenger mRNA. Each tRNA only recognizes one set of 3 nucleotides in mRNA and binds to only one of the 20 amino acids. We form a protein by adding 1 amino acid at a time. The 1968 Nobel Prize jointly went to Nirenberg, Khorana, and Holley. Apart from variations, the genetic codes used by all life forms are very similar. According to the theory of evolution, the establishment of the genetic code occurred very early in life history. The Soviet Union's successful launch of Sputnik 1 in 1957 marked the beginning of the space age and an epic geopolitical race for technological, military, and moral superiority with the United States. The Russians had launched the first animal into space, a dog named Laika on board Sputnik 2, and the US was launching monkeys and chimpanzees, but both governments knew that the next big victory in the space race could only be claimed by launching a person into space. Similar to the original Sputnik effort, the Soviet human spaceflight program, known as Vostok, relied on modifying existing intercontinental ballistic missile rockets to fit a small passenger capsule. The Soviet Air Force secretly screened about 20 pilots to select Senior Lieutenant Yuri Gagarin as the first cosmonaut, space sailors in Russian. At the same time, the US human spaceflight program, called Project Mercury, was on a parallel track, modifying the Redstone missile to accommodate its small single-passenger capsule. They ultimately selected 7 Air Force, Navy, and Marines test pilots, who instantly became celebrities, even before their flights. They chose Navy test pilot Alan Shepard to fly the first Mercury mission. Vostok and Mercury had early unmanned launch failures. Both teams had to demonstrate that their rockets would work with an empty capsule before government leaders authorized a human-piloted flight. Both teams were neck and neck in the race to launch a person first in early 1961, and once again the Soviets scored an enormous international victory by successfully sending Gagarin into space first for one orbit of Earth in Vostok 1 on April 12, 1961. 3 weeks later, Shepard became the second person, and first American, to launch into space with his successful suborbital flight in the Freedom 7 capsule. The Russians had again taken the lead. However, shortly after Shepard's flight, America upped the ante when President John F. Kennedy, in an address to Congress, called for NASA to land a man on the moon before the decade was out. Between 1950 and 1987, the world population doubled from 2.5 billion to 5 billion. This was a startling surge, and humans were already straining food supplies. 1943, for example, 4 million people in India, 6% of the population, died in a famine. During that period of surging population growth, a problem arose. The world had no way to produce enough food to feed everyone at the then current production levels. The Green Revolution, a development that prevented mass starvation and saved 1 billion or more lives, began in 1961. Biologists and engineers worked together to spread advanced agricultural technologies worldwide, championed by American biologist and humanitarian Norman Borlaug, who became a spokesperson for these initiatives. A big factor in improving food production happened at the biological level, by breeding and genetically engineering better strains of cereal grains like wheat and rice. Biologists took an engineer's problem-solving approach. They were trying to breed plants that could make use of more nitrogen, while at the same time putting the nitrogen into grain production, rather than stem construction. The biologists wanted short, stocky stems so the plants would not fall over. They also wanted to reduce the time to harvest. They could pull this off by discovering and incorporating dwarf strains and other useful characteristics to produce high-yield crops. These new strains of plants needed water and fertilizer. Engineers could respond to those needs with irrigation projects and new ways of increasing fertilizer production. Then they went a step further. In warm climates, it is possible to put in 2 crops a year, but only if there is enough water to support the second crop. With the rainy season supplying the water for one crop, a country like India needed a way to store water for the second crop. So engineers built thousands of new dams in India to catch and hold water from monsoon rains. Now India could grow twice as much food. The effect of these improvements was startling. World food production doubled and then doubled again. Even though the population was growing, the food supply grew faster. Science and engineering together created a farming revolution. By the 1930s, physicists had learned to build all matter out of just 3 kinds of particles: electrons, neutrons, and protons, author Stephen Battersby writes. By the middle of the 1960s, scientists had detected 100 supposedly fundamental particles. It was a mess. Through a combination of theory and experiment, a mathematical model called the Standard Model explains most of the particle physics observed so far by physicists. The model groups elementary particles into bosons, often transmitting forces and fermions. Fermions consist of various quarks. 3 quarks represent both the proton and neutrons, and leptons, including the electron and neutrino, which were discovered in 1956. Neutrinos are difficult to detect because they have a minute mass, but not zero, and pass through ordinary matter almost undisturbed. Today, we know about many subatomic particles by smashing apart atoms in particle accelerators and observing the resulting fragments. As suggested, The Standard Model explains forces resulting from matter particles exchanging boson force-mediating particles, including photons and gluons. The Standard Model predicts the Higgs particle as the fundamental particle, explaining the masses of other elementary particles. The exchange of massless gravitons generates the force of gravity, but we have yet to detect these experimentally. In fact, we need to complete the Standard Model to include gravity forces. Some physicists try adding gravity to the Standard Model to produce a grand unified theory, or GUT. In 1964, physicists Murray Gell-Mann and George Zweig proposed the concept of quarks, just a few years after Gell-Mann's 1961 formulation of a particle classification system known as the Eightfold Way. In 1960, physicist Sheldon Glashow's unification theories provided an early step toward the Standard Model. To ancient humans, chaos represented the unknown, the spirit world. Menacing, nightmarish visions that reflected man's fear of the uncontrollable and the need to give shape and structure to his apprehensions. Today, chaos theory is an exciting, growing field that involves the study of wide-ranging phenomena exhibiting a sensitive dependence on initial conditions. Despite the seemingly random and unpredictable nature of chaotic behavior, it frequently adheres to rigorous mathematical rules derived from formulas subject to formulation and study. Computer graphics is a crucial research tool for studying chaos. From chaotic toys with randomly blinking lights to wisps and eddies of cigarette smoke, chaotic behavior is generally irregular and disorderly. Other examples include weather patterns, some neurological and cardiac activity, the stock market, and certain electrical networks of computers. People frequently apply chaos theory to diverse forms of visual art. In science, certain famous and clear examples of chaotic physical systems exist, such as thermal convection in fluids, panel flutter in supersonic aircraft, oscillating chemical reactions, fluid dynamics, population growth, particles impacting on a periodically vibrating wall, various pendular and rotor motions, non-linear electrical circuits, and buckled beams. The early roots of chaos theory started around 1900 when mathematicians such as Jacques Hadamard and Henri Poincaré studied the complicated trajectories of moving bodies. Edward Lorenz, a research meteorologist at the Massachusetts Institute of Technology, used equations to model the atmosphere's convection in the early 1960s. Despite the simplicity of his formulas, he quickly found one of the hallmarks of chaos. Extremely minute changes in the initial conditions led to unpredictable and different outcomes. In his 1963 paper, Lorenz explained that a butterfly flapping its wings in one part of the world could later affect the weather thousands of miles away. Today, we call this sensitivity the butterfly effect. Cognitive behavioral therapy, CBT, which emphasizes the role of errors in thinking in producing negative emotions, has ancient roots. In the Enchiridion, the Greek Stoic philosopher Epictetus penned, "What disturbs men is not the things themselves, but the perspective they adopt." In CBT, the psychotherapist helps the patient think about situations and circumstances in new ways to change the patient's reactions and feelings. If the patient can identify maladaptive or irrational thoughts, the psychotherapist can challenge them. The improved behaviors further educated the patient and reinforced productive thinking. A patient commonly keeps a diary of events and associated feelings and thoughts. In the 1950s, American psychoanalyst Albert Ellis shaped the development of CBT, partly because he disliked classical psychoanalysis's seemingly inefficient and indirect nature. Ellis wanted the therapist to be involved in helping the client modify unhelpful thought patterns. Aaron Beck, an American psychiatrist and psychoanalyst, became the major driving force behind modern CBT in the 1960s. Numerous studies have demonstrated the effectiveness of CBT in treating depression, insomnia, anxiety, obsessive-compulsive disorder, post-traumatic stress disorder, eating disorders, chronic pain, and schizophrenia. A therapist sometimes asks a patient to reframe a thought about a testable hypothesis. In this manner, the patient can step back from the belief to allow more objective examination and arrive at a different view. For example, a depressed person may overgeneralize, concluding she will never get a job after a single failed interview. Sometimes, gradual exposure to a fearful stimulus can decrease the symptoms of phobias and compulsions. We may ask depressed people to schedule small pleasurable activities, such as meeting a friend for coffee. This modifies behavior and tests a belief or hypothesis, such as, "No one enjoys my company." For very serious psychological disorders, one can also use CBT in conjunction with medications. During the 1940s, Wilder Penfield, a renowned Canadian neurosurgeon, treated severely epileptic patients at McGill University's Montreal Neurological Institute by surgically destroying specific brain areas believed to be the origin of the seizure. Before operating, he applied very slight electrical stimulation to discrete regions of the motor and sensory cortex and, with his colleague, the neurologist Herbert Jasper, mapped the body part that responded to stimulation. Together, they constructed a homunculi, little man, map representing specific body parts affected by motor and sensory brain sites. Studies conducted at the California Institute of Technology during the 1960s provided greater insight into brain lateralization, functional specialization. The brain's left and right cerebral hemispheres, sides, are almost identical in appearance, yet very different in carrying out functions. The two hemispheres normally communicate through a thick band of nerve fibers called the corpus callosum. Doctors have severed large portions of this band since the 1940s to treat severe epilepsy, leading to split brain patients. However, these operations are now rare. The psychobiologist Roger Sperry and his graduate student Michael Gazzaniga tested the functioning of each hemisphere independent of the other in split-brain humans and monkeys. Around 1964, they discovered that while each hemisphere could learn, one hemisphere had no perception of what the others learned or experienced. These studies concluded that the left and right hemispheres specialize in performing different functions. The left brain is primarily concerned with analytical, verbal, and language processing tasks, while the right side handles the senses, creativity, feelings, and facial recognition. Sperry received the 1981 Nobel Prize for his split-brain discoveries. Individuals are often characterized as being left-brain or right-brain thinkers. People often characterize left-brain individuals as more logical, fact-oriented, linear thinkers and focused on structure and reasoning, while those labeled right-brained are believed to be feelings-oriented, intuitive, creative, and musical. Although this stimulates conversation at cocktail parties, there is no compelling anatomical or physiological evidence to support these labels, and most scientists regard this characterization as a myth. Welcome to the particle zoo. In the 1960s, theorists realized that we could understand patterns in the relationships between various elementary particles, such as protons and neutrons, if these particles were not elementary, but composed of smaller particles called quarks. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Only the up and down quarks are stable and the most common in the universe. High-energy collisions produce the other heavier quarks. Remember that leptons, particles that include electrons, do not consist of quarks. Physicists Murray Gell-Mann and George Zweig independently proposed quarks in 1964, and by 1995, particle accelerator experiments had provided evidence for all 6 quarks. Quarks have a fractional electric charge. For example, the up quark has a charge of +2,3, and the down quark has a 0C8 charge. 2 down quarks and 1 up quark form neutrons, which have no charge, while 2 up quarks and 1 down quark form the positively charged proton. A powerful short-range color force tightly binds the quarks, mediated by force-carrying particles called gluons. Quantum chromodynamics is the theory that describes these strong interactions. After one of his perusals of the silly line in Finnegan's Wake, 3 quarks for muster mark, Gell-Mann coined the quark for these particles. Right after the Big Bang, the universe was filled with quark-gluon plasma because the temperature was too high for hadrons, i.e., particles like protons and neutrons, to form. The authors, Judy Jones and William Wilson, explain this. Quarks pack a mean intellectual wallop. They imply that nature is three-sided. Quarks, specks of infinity and building blocks of the universe, are science's most ambitious and coyest. The cosmic microwave background, CMB, is electromagnetic radiation filling the universe, a remnant of the dazzling explosion from which our universe evolved during the Big Bang 13.7 billion years ago. As the universe cooled and expanded, wavelengths of high-energy photons, such as in the gamma-ray and X-ray portions of the electromagnetic spectrum, increased, and lower-energy microwaves shifted. Around 1948, cosmologist George Gamow and colleagues suggested that this microwave background radiation might be detectable. And in 1965, physicists Arno Penzias and Robert Wilson of the Bell Telephone Laboratories in New Jersey measured a mysterious excess microwave noise that was associated with a thermal radiation field with a temperature of about 454 F3K. They determined that they were observing the most ancient radiation in the universe, providing evidence for the Big Bang model after checking for various possible causes of this background, including pigeon droppings in their large outdoor detector. Note that because energy photons take time to reach the Earth from distant parts of the universe, we also look back in time whenever we look outward in space. Launched in 1989, the COBE, Cosmic Background Explorer, satellite made more precise measurements determining a temperature of 454.47 DGF, 2.735 K. COBE also allowed researchers to measure small fluctuations in the intensity of the background radiation, which corresponded to the beginning of structures such as galaxies in the universe. With scientific discoveries, luck matters. Author Bill Bryson writes, although Penzias and Wilson had not been looking for the cosmic background radiation, didn't know what it was when they had found it, and hadn't described or interpreted its character in any paper, they received the 1978 Nobel Prize in Physics. Connect an antenna to an analog TV. Make sure it's not tuned to a TV broadcast, and about 1% of the dancing static you see is accounted for by this ancient remnant of the Big Bang. The next time you complain that there is nothing on, remember you can always watch the universe's birth. Every computer needs RAM or random access memory. The computer's central processing unit needs a place to store its programs and data so that it can access them quickly, at the same pace as the CPU's clock operates. For each instruction the CPU, central processing unit, executes, it must fetch the instruction from RAM. The CPU also moves data to or from RAM. Imagine you're an engineer looking at computer memory options in the late 1960s. There are 2 possibilities. The first is core memory, made by weaving tiny ferrite donuts into a wire mesh. Core memory has many problems. It is expensive, heavy, and enormous. The second possibility is static RAM made from standard transistor circuits. Each memory bit requires several transistors, and given the state of integrated circuits at the time, it is only possible to put a small amount of memory on a chip. However, in 1966, American electrical engineer Robert Dennard, who was working for IBM, tried something different to reduce the number of transistors and fit more memory cells on a chip. He explored the idea of dynamic RAM using a capacitor to store 1 bit of data. The capacitor represents a 1 when charged and a 0 when discharged. On the surface, this seems ridiculous because capacitors leak. If you store a 1 in memory made of capacitors and do nothing, the capacitor will leak and forget the 1 in less than 1/10 of a second. However, the advantage is that this approach greatly reduces the number of transistors, increasing the number of memory cells on a chip. We periodically read and rewrite all capacitors, for example every few milliseconds, to solve the leakage problem, thereby refilling all leaking capacitors containing ones with a full charge. In 1970, we introduced this approach, known as dynamic RAM, DRAM, because it requires dynamic refreshment to maintain the capacitor's charge. The dynamic RAM approach produces memory cells that are much smaller and, therefore, less expensive than static RAM. Therefore, every desktop, laptop, tablet, and smartphone today uses DRAM. This is a wonderful example of how engineers can reduce costs by embracing ideas that may seem initially ridiculous. The endosymbiont theory helps us understand evolution because it explains the origin of organelles in eukaryotic cells, those in plants, animals, fungi, and protists. Symbiosis, which occurs at all levels of biological organization, involves two organisms that cooperate for mutual benefit to gain a competitive advantage, for example insect pollination of flowers or the digestion of food by gut bacteria. In eukaryotic cells, mitochondria and chloroplasts are organelles that generate the energy required to perform cell functions. Mitochondria, the site of cellular respiration, use oxygen to break down organic molecules to form ATP, adenosine triphosphate. While chloroplasts in plants, the sites of photosynthesis, use energy derived from the sun to synthesize glucose from carbon dioxide and water. Adding one organelle at a time. The endosymbiont theory states that primitive eukaryotic cells, protists, engulfed small bacteria, alpha proteobacteria, containing mitochondria. In the ensuing symbiotic relationship, the bacterium, now called the symbiont, provided its evolving mitochondria, the energy generator, while the eukaryotic cell offered protection and nutrients. By an analogous process, a eukaryotic cell engulfed a photosynthetic cyanobacterium that, in time, evolved into a chloroplast. This description of primary endosymbiosis depicts the engulfment of one living organism by another. Secondary endosymbiosis occurs when another eukaryote engulfs the product of this primary endosymbiosis. This provides the basis for incorporating additional organelles and expands the environments where eukaryotes can survive. The Russian botanist Konstantin Mereshkovsky, who rejected Darwin's theory of evolution and actively promoted eugenics, first proposed the endosymbiotic theory for chloroplasts in 1905 and expanded it to include mitochondria in 1920. Lynn Margulis, a biology professor at the University of Massachusetts Amherst, and the former wife of the late astronomer Carl Sagan, reintroduced the endosymbiotic theory in 1967, but it gained scientific traction then. 15 journals rejected her paper before they accepted it, marking a significant milestone in endosymbiont theory. For much of recorded history, many doctors saw the human heart as the inscrutable, throbbing seat of the soul, an agent too delicate to meddle with. However, the 1953 invention of the heart-lung machine made the possibility of heart transplantation, replacing a recipient's damaged heart with a deceased donor's healthy heart, a reality. This device could temporarily bypass the heart and lungs during surgery and ensure adequate oxygenation. In 1964, American surgeon James Hardy performed the first heart transplant when he transplanted a chimpanzee's heart into the chest of a dying man. No human heart was available. The animal heartbeat inside the patient was too small to keep him alive, and he died after 90 minutes. In 1967, South African surgeon Christian Barnard performed the world's first successful human-to-human heart transplant, removing the heart of a young woman who had died in a car accident. The recipient was Louis Washkansky, a 54-year-old man with heart disease. A day later, he was awake and talking. The immunosuppressive drugs he was taking to combat the rejection of foreign organ tissue caused pneumonia, which claimed his life after 18 days. In 1972, the discovery of cyclosporine, a fungus-derived compound that suppressed organ rejection, and allowed a significant portion of the body's immune system to function normally and fight general infection, significantly increased the success of organ transplants. The prognosis for heart transplant patients was no longer so bleak. For example, although an extreme case, American Tony Hughesman survived for 31 years with a transplanted heart. Today, transplants can include the heart, kidneys, liver, lungs, pancreas, and intestines. In 1982, American researcher Robert Jarvik implanted the first permanent artificial heart. The Saturn V rocket screams, "Engineering!" From its ridiculous size to its brute force power to the mission it helped accomplish, it is the most amazing rocket ever created. It holds several records, including its 260,000-pound, 117,934 kilograms payload capacity to low Earth orbit. How could engineers create something this stupendous given the technology available at the time? When they conceptualized this rocket, most engineers were still using slide rules. And how did they make it so quickly? In 1957, the United States had never successfully launched anything into orbit. Yet in 1967, this colossus headed into orbit with ease. The F-1 engine was a key player. Engineers started its development for an Air Force project several years before NASA even existed, a fortunate coincidence. This resulted in engine testing and smooth operation before it was necessary. The F-1 is the largest single engine ever created, with a thrust rating of 1.5 million pounds, 6.8 meganewtons. Putting 5 F-1s together in the first stage created 7.6 million pounds of thrust. The rocket, fully fueled and loaded with payload, weighed about 6.5 million pounds, 3,000 tons of cloth. To launch the rocket, each engine burned almost 1 million pounds, 450,000 calories of kerosene and liquid oxygen in less than 3 minutes. Once the first stage disappeared, the remaining Saturn V was 5 million pounds, 2.3 million kg lighter. The second and third stages took the payload the rest of the way to orbit, burning liquid hydrogen and oxygen. At the top of the third stage rested an essential component, a ring called the instrument unit. This ring was almost 22 feet, 7 meters in diameter, 3 feet, 1 meter high, and weighed 2 tons. It contained computers, radios, monitoring equipment, radar, batteries, and other systems to control the 3 stages during flight and communicate with ground control. The microprocessor did not exist, so the brain was a custom-made, triple-redundant IBM minicomputer. Engineers created this disposable behemoth to send men to the moon and then used it to loft Skylab, a true engineering wonder. In the 1950s, there were only a few hundred computers worldwide, but by the 1960s, companies were selling thousands of computers. The minicomputer was born in 1965 with the PDP-8, produced by the Digital Equipment Corporation, DEC. What if you wanted to use a computer? You needed a terminal and a dedicated communication line. To use 2 computers, you need 2 terminals and 2 lines. People began to consider connecting computers to networks to allow access to multiple machines. Electrical engineers developed hardware that digitized voice signals and transmitted them as digital data. The T1 line, invented in 1961, could carry 1.5 million bits per second, enough bandwidth for 24 phone calls. Once phone lines could transport digital data, they facilitated the connection of computers and enabled the implementation of various services that leverage these computers and their connections. This organization gave birth to the Internet. The first Internet-like computer interconnection occurred in 1969, when 4 computers connected under ARPANET, Advanced Research Projects Agency Network, using concepts and ideas developed by American engineer Paul Barron, Welsh scientist Donald Davies, and Lawrence Roberts of the Lincoln Laboratory. Then, this tiny network started growing. By 1984, the number of host computers had hit 1,000. By 1987, the number was 10,000. NCP, Network Control Program, and IMPs, interface message processor, were important technologies for the early internet. Together, these technologies created what is known as a packet-switched network between all the computers. When a host computer wanted to send something to another, it would break the information down into small data packets and hand the packets, along with a destination address, to its IMP. When the IMP worked with other IMPs, it would deliver packets to the desired recipient computer. The two computers had no idea how the packets would travel over the network, nor did they care. Once they arrived, they would reassemble the packets. Eventually, TCP/IP, Transmission Control Protocol Internet Protocol, would replace NCP, and routers would replace IMPs. At that point, engineers had created the internet as we know it today. When we think about engineering, we generally think about creating a new object, a new building, a new device, a new mechanism. Genetic engineering is a different type of endeavor. These experiments involve tinkering with a genome, a complex system we must fully understand. To create new behaviors, genetic engineers add new genes to a genome. The predecessor to genetic engineering is selective breeding, in which breeders select desired traits. With selective breeding, we have created all the various breeds of dogs. However, genetic engineering, which appeared in 1972, when American biochemist Paul Berg created the first recombinant DNA molecules, is different. Engineers inject new genes into genomes in a way that nature could never accomplish. For example, Berg combined two viruses. Other recent applications include the addition of a jellyfish gene that produces a green fluorescent protein in either a fish or a mouse, thereby creating fluorescent mice. Soybean plants receive a gene that renders them immune to a herbicide, preventing it from killing them. In one of the most bizarre examples, genetic engineers added genes to produce spider silk in goats. Spider silk proteins appear in a female goat's milk. The goal was to extract the proteins to create strong, highly elastic materials. There are different ways to inject the genes of one organism into another, and the gene gun is one popular tool. The technique is so simple that its effectiveness is astounding. In liquid form, we add the gene for injection to tiny particles of tungsten or gold. A shotgun-style gun shoots particles at a petri dish full of target cells. The particles puncture some cells but do not kill them, allowing them to absorb the new gene. Genetic engineers can create new organisms by injecting genes from one organism into another. One of the most beneficial examples is the production of human insulin by E. coli bacteria, which was developed in the 1980s. Millions of people now use genetically engineered insulin. Simple formulas can produce amazingly diverse and chaotic behaviors, while characterizing phenomena ranging from animal populations, rise and fall to certain electronic circuits' behavior. One formula of special interest is the Logistic map, which models population growth. Biologist Robert May popularized it in 1976, drawing on the earlier work of Belgian mathematician Pierre-François Verhulst, 1804-1849, who studied models of population changes. The population may undergo many behaviors depending on the R value, which controls the growth rate and starvation. For example, as R increases, the population may converge to a single value or bifurcate, so that it oscillates between 2 values, then oscillates between 4 values, then 8 values, and finally becomes chaotic. Thus, slight changes in the initial population yield unpredictable outcomes. The ratio of the distances between two successive bifurcation intervals approaches the Feigenbaum constant, a number discovered by American mathematical physicist Mitchell Feigenbaum in 1975. Interestingly, although Feigenbaum initially considered this constant for a map similar to the Logistic map, he also showed that it applied to all one-dimensional maps of this kind. This implies that a multitude of chaotic systems will bifurcate at an identical pace, thereby enabling the use of his constant to forecast the onset of chaos in these systems. We discovered this kind of bifurcation behavior in many physical systems before they entered the chaotic regime. One of the most important accomplishments of social development is the ability to imagine what other people feel or think and respond accordingly. Modern developmental science has studied this ability in infants, children, chimpanzees, and even rodents for about 30 years. Developmental psychologists call this ability theory of mind, TOM. Several of the world's major religions hold this principle, but in psychology, David Premack and Guy Woodruff offered one of the first full expressions of TOM in 1978. Formally, theory of mind refers to children's understanding that others also have thoughts, beliefs, objectives, and emotions. Without TOM, the child would not be able to pick up on the social cues or intentions of others, as is often the case when a child has autism. The theory of mind is a developmental process that is usually fully in place in normally developing children by about age 4 or 5. Scientists have discovered that infants learning simple tasks like pointing or reaching can direct others' attention and trigger the critical precursors of the theory of mind, TOM, as early as 7 to 9 months. By the end of the first year, infants begin to understand that people have intentions. Children only realize that others' feelings and thoughts affect their actions at age 4 or 5. Neuroscientists using brain imaging techniques have shown that this is exactly the age when the prefrontal cortex of the brain is rapidly maturing. For children with autism, this is not the case, although there are interventions that can help improve the brain's responses in children with autism. The theory of mind is crucial for displaying empathy and caring for others. It makes it possible for us to be socially competent. Research on TOM has greatly facilitated our understanding of children's social development, with implications for emotional and cognitive development. It is also a principle that promotes mirror neuron reception. Albert Einstein's early 20th century theory of general relativity fundamentally curtails space and time near extremely massive objects. Einstein and others predicted that due to the curvature of spacetime, the gravitational field of massive foreground objects would bend light from distant objects. Arthur Stanley Eddington, a British astrophysicist, confirmed the prediction in 1919 when he noticed that stars observed near the Sun during a solar eclipse were slightly out of position. Einstein continued to study this effect in the 1930s, and he and others, including the Swiss-American astronomer Fritz Zwicky, speculated that more massive objects, such as galaxies and clusters of galaxies, could bend and amplify light from distant objects almost as a lens bends and magnifies normal light. However, it took many decades for astronomers to find observational evidence of such gravitational lensing. In 1979, astronomers at the Kitt Peak National Observatory in Arizona discovered the first example of what appeared to be twin quasars, two active galactic nuclei very close to each other in the sky. A foreground galaxy's strong gravitational field bent and split the light of the two quasars into two parts. Since then, researchers have discovered numerous additional examples of gravitational lensing, suggesting 3 possible mechanisms for the effect to occur. Strong lensing forms distinct multiple or partial images, typically arc-like. Weak lensing has been detectable by observing small and subtle shifts in star or galaxy positions over large regions. In microlensing events, the gravitational lensing effect of a large foreground mass, such as another star or galaxy, temporarily amplifies the brightness of random distant stars, or even planets. Initially, researchers discovered and studied gravitational lenses as accidental, serendipitous events. However, scientists have intentionally conducted several astronomical surveys to search for gravitational lensing events. These surveys aim to obtain unique measurements of the properties of distant galaxies that would not be visible without the lens amplification, as well as the properties, such as mass, of the lensing galaxies and clusters themselves. The Big Bang theory states that our universe was in an extremely dense and hot state 13.7 billion years ago, and space has been expanding ever since.